Hello everyone. Today I'm going to discuss the last problem of Leetcode Weekly Contest 441, which is count beautiful numbers. So what is the problem? We are given two positive integers L and R, and we have to find all the count of beautiful integers between the range L to R inclusively. Okay. So what is a beautiful integer? Beautiful integer means that if the product of the digits of that integer is divisible by the sum of its digits. So let's consider the input 10 to 20. The beautiful numbers in the range are 10 and 20. So uh, for 10, what is the product of the digits? Product of the digits is 0. And what is the sum of the digits? Sum of the digits, let's call it P, and sum of the digits, let's say S. Sum of the digits is 1. Then product is divisible by sum. Similarly for 20, the product is divisible, product is 0, and sum is 2. So product of the digits are divisible by sum of the digits. So these two are beautiful integers in the range 10 to 20. Okay. For 1 to 15, the first 10 integers 1 to 10, where the sum of the digits is same as for 1 to 9, the sum of the digits is same as product of the digits, like for single digit integers, like for 1 to 9 the product will be same, 1 to 9, and the sum will be same, 1 to 9. So product of the digits is divisible by sum of the digits, and for 10 also it is divisible by sum of the digits. So answer is 10. 1 2 3 4 5 6 7 8 9 10. Now how we are going to solve this problem? The brute force way to solve this problem will be to iterate over every integer from L to R and find their sum of the digits and their product of the digits. Okay, so if we go by brute force approach, just for explanation, the time complexity will be order of R minus L into what we can say, the length of the every in any integer will be at range 10. So the overall time complexity will be the number of integers between R and L into 10. Okay, but here you can see that L and R are at the range of 10 to the power 9. So this is definitely not possible. Our brute force approach will not be possible. So how we are going to solve this problem? So for when we encounter this type of what we can say, constants where L and R are in the range 10 to the power 9, we think about solving this problem digit wise, and we call this approach digit DP. Okay, digit DP, this is very important concept for competitive programming. Digit DP, what digit DP is? Digit DP is when we iterate the integer digit by digit. Okay, we iterate the integer digit by digit. Okay, so what are the uh, parameters of a recursion state in the digit DP? The first parameter will obviously be the index we are currently at. So let's say our integer is, let's say, 100. Okay, let's say our integer is 100. Then let's say we are at the 0th digit. Okay, 0th digit, we will iterate from left to right. So let's say we are at the 0th digit. Then this will be pointed by I. Okay, now let's say I1. Now another two important parts for this problem is, one is the SOD, like the sum of the digits, we can call it SOD. And another thing is important to us is the product of the digits. Okay, sum of the digits and product of the digits. Okay, now there are other parameters also, but I will explain why only taking SOD and PRO will not help us. So what is the range of PRO? Okay, so PRO means the product of the digits. Now let's say product of the digits could be like every digit, let's say, is 9, and there are 10 9 nines possible. Then the range of product of the digits could go from 0 to 0 to 9 to the power 9. Okay, so 9 to the power 9 is definitely not possible, so we can't really take product. So instead of taking product, we can take product modulo sum of the digits. But we are taking product modulo sum of the digits, but we don't really know what the sum of the digits is. Okay, because we are when we are jumping to the one digit to another, the sum of the digits is changing. Okay, so that's why we'll take this sum of the digits as constant. Okay, we'll take this sum of the digits as constant, and another variable we'll take is that current sum of the digits. We can call it current sum of the digits. And at the base case, so base case will be I is equals to length of the integer, length of the integer. Let's say our integer is, let's say, S, then I is equals to length of the integer. Then if this product is beautiful, this integer is beautiful, how we can identify the this will be beautiful only if we are taking modulo SOD. So the current SOD at the end, the current SOD should be equals to our SOD, because we are fixing our SOD and we are saying that this will be the SOD of the beautiful integer. So current SOD is equal to SOD, and another condition is that our product should be equals to 0, because we are taking product modulo SOD, right? So at the end the product should be equals to 0. This is the base case. Or if these two conditions satisfied, then we can say that this is a beautiful integer. Now these four are required: I, SOD, product modulo SOD, and C SOD, current SOD. Okay. Now another thing, for any digit DB problem, that is, if you have solved this problem, you might have known that. But if you don't know, let me explain to you that another thing is important, which is a flag. Okay. So what flag identifies? Okay. Let's say, um, let's say AC is something like 159. Okay. AC is something like 159. Now here for the first digit, if the flag is set to 1, for the first digit we can take from 0 to 1, right? For the first digit we can take from 0 to 1, and let's say in the first digit we have taken 1, the next digit we can take from 1 to 5, sorry, 0 to 5, right? 0 to 5. Let's say we have taken 5 in the let's call it 158, right? Let's say this is 158. So let's say in the first digit we have taken 1, in the second digit we have taken 5, in the third digit we have to take from 1 to 8. We can't really take 9. But let's say in the second digit we have taken, let's say, 3. Okay. So if in the second digit we have taken 3, then in the third digit we can take 9 also. So that flag identifies that our let's call it F identifies that this uh, n digit is strict or not. If f equals to 1, if let's say if f equals to 1, then we can only take till s of I, and if f equals to 0, we can take till 9. Okay, take till 9. I hope you get it. Strict means, f means the strict means we can take till si, but if it is not strict we can take till 9. Okay, that another parameter f will get identified here. So now this is the recursion state, the recursion parameters. Now how we are modifying that, I will explain that in the code. Now I will explain the time complexity. So for recursion state, how we calculate time complexity, we take the total number of possibilities. So for I, total number of possibilities are from length of the string, length of the integer, it is 10. Okay. For SOD, this could be 9, all nines, 9 nines. So SOD could be 81. Product similarly is we are taking modulo, so product similarly could be 80, you can say 80, and current SOD is can also go to 81. Okay, and if is a flag, so it will be either 0 or 1. So we can say that it is around in the range 10 to the power 7. Okay, so this is definitely possible, 10 to the power 7, and it is definitely possible. So I will jump into the code now and I will explain how the transitions are happening in the recursion states. Okay, now I have declared the digit dp I, flag, SOD, sorry, this is current SOD, this is SOD, and this is the product. Now base case is I, so here instead of going to I to I plus 1, I am coming from I to I minus 1. I will explain why I am doing that. Okay. Now if I equals to 0, that means we have come to the end. The base case, we are checking that I have already explained that the base case will return 1 if product equals to 0, and the current SOD is equals to SOD. Okay, let me take one moment, right? Okay, now our current ending is 9. Now if it is strict, I have already explained, if the flag is strict, we'll take end as D. Okay, now here you can see that I am taking I is not, we are not exactly taking si, instead of we are taking s of n minus I. Why I am doing that, I will explain to you later. Okay, now we are checking that, or in the first digit we can't really take 0. Okay, in the first digit we can't really take 0. So how we can identify this as a first digit? If the current SOD is 0, then we can say, definitely say this is the first digit. Okay, so if current SOD is 0, then we will start from 1, otherwise we will start from 0. Or in flag is flag. Now if flag is 1 and current digit is less than the digit in the s, okay, current digit is less than the digit in the s, our flag will be changed to 1, right? Let's say here I have explained it. In the second digit, let's say we have taken 0, 1, 2, 3 or 4. the current digit 3 or 4 will be less than 5, then our new flag will be 0. Okay, our new product is product, and we can directly take in product as product into j modulo sot, and this is not needed. Okay, and we're doing I minus 1 new flag. The current sod will be incremented by j, the digit we have taken. Sod will not change, this is a constant, and new product. Okay, now why we are taking this I, why we are doing from backwards? Okay, because we are fixing the length. Okay, we are fixing the length because let's say we have 123, right, and we have to count all the integers. So there could be beautiful integers of length 1, there could be beautiful integers of length 2, and there could be beautiful integers of length 3. Okay, so we are fixing the length. Okay, we are fixing the length. So if I equals to 1, that means if we start from I equals to 1, then we'll only consider length integers with length 1. If I is 2, we'll only consider integers with length 2. Similarly for 3. Okay, now this is the base case. We are resetting the dp, and we are taking rs as an ls. So for we have to find all the integers between r and l, r to l, sorry, l to r. So for l to r, what we will do, we will count all the beautiful integers from 1 to r, and we will count all the beautiful integers from 1 to l minus 1, and if we take the difference between them, we will get the beautiful integers from l to r. Okay, I hope you get it. And this is the thing, rs is string value of r, and ls is string value of l minus 1. So our recursion will give us count of beautiful integers from 1 to s. Okay, now we are iterating over all the possible values of sod from 1 to 81, and we are iterating all the values of the length of the beautiful integer. Okay, length of the beautiful integer rs. Okay, now our flag value will be 1 only if our length, let's say our length is 1, then we don't really need strict bound. Okay, we don't really need strict bound, because let's say 1 to 9 is obviously less than s. So in that case, our initial flag value will be 0. So only if j is equals to rs size, then our value will be 1, flag value will be 1, otherwise our flag value will be 0. Okay, so we have calculated r answer for r and l answer for l minus 1. If we take the difference between them, we will get our desired answer. I hope you got the explanation. I'll attach the code link in the description box. If you have any doubt in any part of the code or explanation, you can always ask in the comment section. I'll try to reply each and every comment. If you find this video helpful, please like the video, subscribe to the channel, and also share among your peers. Thank you.